In section 1.2, we're going to learn about essential functions. These are the functions that you should be familiar with and already have an idea of how to graph them. The first is a linear function. Linear functions were presented as y equals mx plus b in algebra. We will look at them in function notation. You can think of that as f of x equals mx plus b. Next is a quadratic function. A quadratic function is of the form f of x equals a x squared plus bx plus c. A third degree polynomial function, we'll call that a cubic, looks similar to the quadratic, and we're going to write that as a sub 3 x cubed plus a sub 2 x squared plus a sub 1 x plus a sub 0. So instead of continuing through the alphabet A, B, C, D, E, F, instead we choose to label with subscripts. Now this indicates that the coefficient of each term could be different, so that's why we have different labeling for each coefficient. These two will appear quite frequently. You should be familiar with a quadratic. It looks like a parabola, and that parabola opens up when the leading coefficient is positive. It opens down when the leading coefficient is negative. In the case of a cubic, a graph of a cubic will look something like this when the leading coefficient is positive, and then flip that over when the leading coefficient is negative. We would continue this pattern with a fourth degree polynomial. You call that a quartic. F of x equals a sub 4 x to the fourth plus a sub 3 x to the third plus a sub 2 x to the second plus a sub 1 x plus a sub 0. So each of these coefficients does play a role in how the graph looks, but the basic graph of a fourth degree polynomial is that of a W or an M. So I'm going to draw like this a fourth degree. This is when the leading coefficient is positive. It takes on the form of something like a W, and then if the leading coefficient is negative, it looks more like an M. So these types of graphs you should be familiar with. If it is not something you're familiar with, then again, I encourage you to use your graphing calculator and look at the examples and the homework on your graphing calculator, every single one of them, until you get used to what they look like. A root function is a function of the form x to the 1 over n, where n is an integer. So you might be more familiar with seeing it as the nth root of x from algebra, meaning if n were equal to 2, that means f of x would be the second root of x, which is the same as the square root of x. And the graph of the square root of x, you should know, the basic graph starts at the origin and increases from there. I'll just continue with another. If n were to be equal to 3, that means you would have the function the cube root of x. And this is something that we'll see in calculus, but you may not have encountered it very much in algebra. The cube root of x graph looks like this. So it is the inverse of x cubed. So if you go back up top and look at the x cubed graph right here, you'll notice it's just flipped over and to have the cube root graph. So those two are related that way. They're inverse functions of each other. The reciprocal function you will come to know and love, and that's because it's going to help us out a lot. The reciprocal function, the basic function, it has a graph like this, where in the first quadrant we have decreasing in this manner, so that term is concave up and decreasing. and in the third quadrant is concave down and decreasing. So it's always decreasing. Notice how we have a vertical asymptote at x equals 0. So you might think of that vertical asymptote from time to time. A rational function is similar to a reciprocal function, but the rational function has a function in the numerator and a function in the denominator, and those functions are polynomials. So I'll write that, where P and Q are polynomials. This is perhaps the most interesting type of graph we could end up with. It has vertical asymptotes wherever the zeros of Q are. So I'm just going to suppose that I have zeros for Q here and here. So a typical graph of a rational function might look like this. So it might have a piece over here and a piece over here, and then in the middle something funny happens. So maybe it might be like kind of look like this. So as you may remember, there's also a horizontal asymptote, but by definition, horizontal asymptotes are not going to be reflected in this curve in the middle, because horizontal asymptotes are defined as what is occurring to the output as the input approaches infinity or approaches negative infinity. So right near the origin, we don't expect the curve to respect that horizontal asymptote. Okay, so these are the essential functions that we're going to encounter, and it will be helpful if you are familiar with the behavior of their graphs. The nature of their domains will help you tremendously, and the nature of the range. So make sure you're practicing entering those into your calculator and taking a look at them. If you don't know what they look like, put them in your calculator while you're at home.